In this video, we're going to learn about polar versus nonpolar molecules, and we'll learn how to identify whether a molecule is polar or nonpolar. A nonpolar molecule is a molecule where the atoms and the electrons are arranged symmetrically in the molecule, and it makes the molecule insoluble in water. And the examples that I have here, this one here is methane. So we have a carbon atom with 4 hydrogen atoms bonded around it. It's completely symmetrical. There's no imbalance in arrangement of atoms around the carbon. The next example here is oxygen. So again, we have 2 oxygen atoms on either end, so they're exactly the same. And then we also have some lone pairs of electrons, but they're evenly spaced around the molecule. So this one also is symmetrically arranged. And then our third example would be carbon dioxide. Same thing, we have a carbon in the middle, and on either side is an oxygen atom, so it's symmetrically arranged as well. So that makes it nonpolar. Polar molecules, on the other hand, have an asymmetrical arrangement of atoms. So because of that, there's an unequal sharing of electrons or of electron pairs, or there's lone electron pairs, and the molecule will end up with a partially positive end and a partially negative end. And these are called dipoles. And polar molecules are soluble in water because of this unequal arrangement. So if we look here, we have water, so H2O. And if you take a look, oxygen has lone pairs of electrons on one side. And it also has a stronger affinity for the electrons that it's sharing with hydrogen too. So it pulls the electrons towards itself, like so, and that's what those arrows are demonstrating. And that makes oxygen slightly negatively charged. So this symbol here means that's a negative dipole. And then down here, the hydrogens, because the electrons are being pulled away from itself, has a positive dipole. And that's how we represent it. And then over here, hydrogen chloride, same thing. Chlorine has a stronger affinity for electrons than hydrogen. So even though it's not sharing very equally. So it's hogging the electron in the shared pair. And that gives hydrogen a positive dipole and chlorine a negative dipole. So because of that, they can interact in water with those dipoles. And we'll talk more about that when we talk about water. Intramolecular forces are forces of electrostatic attraction within a molecule. And these forces of attraction hold the molecule together. And it's actually the bond itself that's in the molecule holding it together. That's what intramolecular forces are. And these forces have to be broken by chemical means. So when a chemical reaction happens, those bonds are broken, atoms are rearranged, and we form new compounds and new molecules. So the example that I'm showing here, hydrogen chloride again. So we have our hydrogen atom and our chlorine atom, and they're sharing a pair of electrons, and that would be the intramolecular force. It's the covalent bond that's between the two atoms. Now, in an ionic compound, it would be the same thing. The intramolecular force would be the attraction between the two in the ionic bond. Intermolecular forces are forces of electrostatic attraction between molecules. So if we take a step backwards and we look at the breakdown of the word, inter means between, and intra, the example we talked about before, means within. So anytime you see inter, it's something between, and intra is within. Intermolecular forces are much weaker than intramolecular forces, and they can be affected by physical changes. So a temperature change may cause the forces to weaken or strengthen depending on whether the molecules are getting closer to one another or farther apart. So in this example, again, I'm using hydrogen chloride. If we had 2 of those molecules hanging out together, the positive dipole of hydrogen would become slightly attracted to the negative dipole of an adjacent chlorine atom. And what we end up with is a force of attraction called the intermolecular force. And we're going to learn about the different types of intermolecular forces in the next few minutes. And we will start with the weakest one. So the first of the 3 intermolecular forces is Londen dispersion forces. And in this example, the electrons of one molecule become attracted to the nuclei of neighboring molecules. So if you take a step back to the structure of the atom, remember the nucleus has protons and neutrons within it. And protons are positively charged, and electrons are negatively charged. So the electrons are going to be attracted to the positively charged nucleus. And Londen's dispersion forces are the only forces used to hold nonpolar molecules together. And these are also sometimes called van der Waals forces. Now, if you look at this diagram down here, we have two helium atoms really close to one another. And you can see that there's actually some repulsive forces and some attractive forces at play. So it's like Londen forces, there's some attraction, but it's kept at an arm's length. So if you take a look, these are electrons. They're negatively charged, and we know that like charges repel. So the electrons in the two electron clouds would repel each other. However, they'll also be attracted to the nucleus of the adjacent atom. So there is some repelling, but there's also some attraction going on at the same time. Our next type of force are dipole-dipole forces, and these forces are stronger than Londen forces, and they occur between polar molecules. And in this case, negative dipoles are attracted to positive dipoles. So again, we're looking at our hydrogen chloride molecule right here, and we've got a positive dipole on hydrogen. It's going to become attracted to a negative dipole of a chloride ion in a neighboring molecule. And then same thing over here, this dipole is being attracted to that dipole, and it would go on and on and on throughout the solution. Our final type of intermolecular force, and the strongest one, is hydrogen bonding. And this is a type of dipole-dipole interaction that's between a hydrogen atom in one molecule and either fluorine, oxygen, nitrogen, sulfur, or phosphorus in another molecule. And like I said, it's the strongest of the intermolecular forces. So in this example, we can see water exhibiting this hydrogen bonding. So this negative dipole on oxygen is attracted to a hydrogen, and this hydrogen is being attracted to another oxygen, and so on and so on. So this hydrogen bonding actually gives water some very unique properties, which we'll talk about later in this video. So hydrophilic molecules, if we break down that word, hydro means water, phile or philic means lover of. So if you are hydrophile, you love water. So water-loving molecules. And hydrophilic molecules dissolve in water, or they interact with water. And hydrophilic molecules would include polar molecules and ionic compounds. So in this example here, we have water, which is represented by the red and white molecules. And then we have a salt compound. So we have a crystal of salt here, sodium chloride, and over time, the chloride atoms are going, or chloride ions are going to interact with the positive dipoles of water, and the sodium ions are going to interact with the negative dipoles of water, so with the oxygen end of the molecule. And this would just happen over and over again. And that would be a hydrophilic molecule. So ionic compounds and polar molecules are hydrophilic. Now, hydrophobic molecules are considered water-fearing molecules, so hydro, water, phobia, a fear of. So these molecules are repelled by water and or other polar molecules as well. And they will be attracted to other nonpolar molecules. So lots of nonpolar molecules can interact with each other, but they cannot interact with water. And you can see that in this example. So oil and water, you know, doesn't mix well together. They just form globules or droplets and then rise to the surface if you try to mix water and oil. And then here's another example where we have a leaf with a bead of water on top because the leaf has a waxy cuticle, and wax is hydrophobic as well, so the water can't dissolve onto the leaf surface.